Hello class, you're welcome to our chemistry class. And in chemistry, we shall be looking at the topic entropy and Gibbs free energy. This is a continuation of the topic on enthalpy. Now, enthalpy change is capable of explaining the fact that all exothermic reactions are spontaneous and not all endothermic reactions are spontaneous. Now, when we talk about a reaction being spontaneous, we are saying that the reaction has a potential to occur on its own without the assistance of any external agent. And so if you have a reaction such as A plus B leading to C plus D, a spontaneous reaction is one that is able to proceed without any external agent such as heat, pressure, or the likes being added to it. Now, it is generally observed that most chemical reactions which occur spontaneously increase or decrease the degree of disorder or randomness of a chemical reaction. So a reaction that is spontaneous, when it is spontaneous, there will be an increase in disorderliness. And this increase in disorderliness brings us to what entropy is. So entropy is defined as the measure of the degree of disorderliness or randomness of a system. And entropy is represented as S, where standard change entropy equal to the standard change in entropy of the product minus the standard change in entropy of the reactant. So when we subtract the entropy of the reactant from the entropy of the product, we will get the standard entropy of a particular reaction. Now, the SI unit of entropy is in joules per Kelvin. So if you have a solid, e.g. ice block, which is being heated into liquid, we will find out that the heat that is added to the ice causes the molecules to be in motion and breaks into liquid, which is water. Hence, there's an increase in entropy. Then, when you apply further heat, it will turn into gas, and that is water vapor. Now, what we are saying here is that entropy increases from solid to liquid and then liquid to gas, while the reverse is the case. That is, entropy decreases from gas to liquid and then liquid to solid. The fact that entropy increases from solid to liquid means that we have a positive entropy, right? And if entropy decreases, it means that we have a negative change in entropy. So a positive change means that we have a higher degree of disorderliness. So there's an increase in disorderliness. While if you have a negative, it means that there is a decrease in disorderliness. Examples of processes in which we have entropy change increase include process of melting solid into liquid, or breaking down of large molecules into smaller molecules, or cases of dissociation of a particle, or a case of evaporation whereby this water turns into gas. And examples of processes in which entropy change decrease include condensation, that is the process whereby this gas condenses into liquid and then from liquid it freezes. That's another process. Other process is the formation of precipitate and combination of simple particles or molecules forming complex ones. Now, entropy change in a reversible process is calculated as delta S equal to Q over T, where Q represents the quantity of heat of the system and T represents the temperature. So this is the quantity of heat and this is the temperature. Now, we use this particular one when we are discussing reversible processes. And next, we move on to Gibbs free energy. When we talk about Gibbs free energy, it is talking about the amount of useful work that can be obtained from a system at constant temperature and pressure. Hence, Gibbs free energy is defined as the amount of useful work that can be obtained when a work is being carried out. And we could have Gibbs free energy, the standard Gibbs free energy, to be equal to the standard Gibbs free energy of the product minus the standard Gibbs free energy of the reactant. And then we have a formula that relates the Gibbs free energy, entropy, and enthalpy, which is delta G equal to delta H theta minus T delta S, where this is the standard Gibbs free energy. So this is Gibbs, and here we have our enthalpy, and here delta S is the entropy. Alright, so we have minus over here, which multiplies temperature. Hence, we will be using this particular formula. Now let's take note that for a reaction to be spontaneous, we said that the entropy is positive, and while it is positive, then the Gibbs free energy will be negative. Hence, we have that when the change in Gibbs free energy is negative, it is spontaneous, while when the change in Gibbs free energy is positive, it is not spontaneous. You can place it beside this by saying that when delta G is negative, it means that delta S is positive. And so from here, we can summarize a spontaneous reaction and a non-spontaneous reaction like this. We would say that for a spontaneous reaction, delta S is positive, while delta G is negative. While for a non-spontaneous reaction, delta S is negative and delta G is positive. These are explanations for why a reaction will occur. So now let's solve questions. Here's the first question, which says nitrogen gas reacts with hydrogen gas to form ammonia gas. Given that the standard entropies of nitrogen, hydrogen, and ammonia gases are 192, 131, and 193 joule per Kelvin per mole respectively, calculate the standard entropy change of the reaction. From this question, we're told that there's a reaction between nitrogen gas and hydrogen gas to produce ammonia gas. So first is that we need to balance this equation. We have 3 over here and we have 2 here. That balances the equation. And we have all these as gas. Next, we're told that the standard entropies of each. So for nitrogen, we're given the entropy as 192. For hydrogen gas, we're given as 131. And for the product, ammonia, we're given 193, which is respectively. To find the standard entropy change for the reaction. And so we have it that the standard entropy change for the reaction equal to the entropy change for the product minus the entropy change for the reactant. For the products, we have 193, which is per mole. But here we have 2 moles, so we multiply by 2. Right? So minus for the reactant, which is the 2 of them. Now for nitrogen, we have just 1 mole of nitrogen, which is 192 plus. Then for hydrogen, 1 mole is 131. Then multiply by 3. So we have 3 times 131. And so we have 2 multiplies by 193. That's 386 minus 192 plus 3 times 131, that gives 393. So we have 386 minus 585. Hence, we have a negative entropy, which is 199. 199 joules per Kelvin per mole. Now, since the standard entropy change is negative, it shows that there's a decrease. So it is not spontaneous. It's not spontaneous because we have a negative value of standard entropy change of the reaction. Here's the next question. It says that calculate the entropy change for the reaction and comment on the sign of the value. Hydrogen gas plus chlorine gas to give hydrochloric acid. Given that the standard entropy of hydrogen is 131, standard entropy of chlorine is 223, and the standard entropy of hydrochloric acid is 187. Alright, so first we'll take our equation, which is hydrogen gas reacting with chlorine gas to produce hydrochloric acid. Now we balance the equation by placing 2 in front of hydrogen. Now we have that the standard entropy of the reaction equal to the standard entropy of the product minus the standard entropy of the reactant. For the product, which is hydrochloric acid, we're given 187. So we have 187, which is per mole. But here we have 2 moles, so we multiply by 2. Then minus for the reactant, for hydrogen, we're given 131 plus the other reactant, which is chlorine, we're given 223. So 223. Now we have 2 multiplies 187, that is 374, minus 131 plus 223, that gives 354. And so when we subtract this, we will have 20 joules per Kelvin per mole. Now this is a positive entropy, and a positive entropy means that there is increase in randomness, and that means it is what? It is spontaneous. It can occur without any external agent. Next question, which says calculate the standard entropy of melting point of ice if its melting point is 0 degrees Celsius, given that the standard entropy of melting is 600 joule per mole. We have ice which is melting into water at 0 degrees Celsius. So our attention is on the temperature, which is 0 degrees Celsius, which needs to be in Kelvin, and that's 0 degrees Celsius is the same thing as 273 Kelvin. Alright, and then we're told that the standard entropy of melting, that is standard entropy of melting, equal to 6000 joule per mole. This is a reversible reaction because we have this ice which melts into water, and the water can still freeze back into ice. And so in this case, to calculate the standard entropy of melting, so we have it that the standard entropy of melting equal to the quantity of heat, which in this case it is the entropy over the temperature. Now we have the entropy to be 6000, so we have 6000 over here divided by 273. Now when we divide this, we'll end up having 21.98. So 21.98 joule per Kelvin per mole. That is the standard entropy of melting of the ice at 0 degrees Celsius. Here's a question on Gibbs free energy. Calculate the standard free energy change for the reaction at 25 degrees Celsius, where we have nitrogen react with hydrogen to form ammonia gas. Given that the standard entropies of nitrogen, hydrogen, and ammonia gases are 192, 131, and 193 joule per Kelvin per mole respectively, comment on the sign of the value of delta G of the reaction. Alright, so the first thing we need to do in this question is to get our equations. We have nitrogen gas which reacts with hydrogen gas to produce ammonia gas. So the first thing we need to do is to get a balanced equation. When we place 2 here and we place 3 here, that balances the equation. So we have 6 atoms of hydrogen here, and we have 6 here, we have 2 and 2 over here. And then we have all these as gases. We are told that the standard enthalpy of the reaction is minus 92.4 kilojoules per mole. And we are given that the entropies for the gases, we have 192 for nitrogen, we have 131 for hydrogen, and we have 193 for ammonia gas. The first thing we need to do is to find the standard entropy of the reaction. When we get that, we'll use that along with this standard enthalpy to derive our Gibbs free energy. So we have that the standard entropy equal to the standard entropy of the product minus change in entropy of the reactant. For the product, we have 193. For the product, we have 2 moles of it, so we multiply by 2. Minus for the reactants, we have 1 mole of nitrogen, which is 192, plus the other reactant we have hydrogen, which is 131. We have 3 moles of it, so we multiply by 3. So this will produce 386 minus 192 plus 131 multiplied by 3, that gives 393. And when we add all this together, we'll have minus 199 joules per Kelvin per mole. Next, we have that delta G equal to delta H minus T delta S. That is the standard Gibbs free energy equal to the standard enthalpy minus T delta S. That is the standard entropy. Now, there are some other things that we need to take note of. If you look at the enthalpy, we're given in kilojoule per mole. And when we look at this entropy, we got our answer in joule per kilogram per mole. Now, this kilo means that there's 1,000 over here. So what we could do is to have this also in kilojoules. And when we convert to kilojoules, we'll have minus 0.199 kilojoule per Kelvin per mole. So this is the entropy that we are going to use. So that's minus 0.199. Now let's proceed. We have our delta G, which is equal to the delta H, that is minus 92.4, minus the temperature, which is 298, multiplied by delta S, which is minus 0.199. So we have minus 0.199. It's better we have this in brackets like this. Now when we multiply that out, we have minus 92.4 minus 298 multiplied by minus 0.199, and that will give us minus 59.3. So we have minus 59.30 here. So we have minus 92.4 minus times minus gives us plus 59.30, and minus 92.4 plus 59.3, that gives minus 33.1. So minus 33.10 kilojoule per mole. So this is the standard Gibbs free energy. A negative value over here indicates that the reaction is a spontaneous reaction. Here's the next question. Calculate Roman figure 1, the standard enthalpy change. Roman figure 2, the standard entropy change. Roman figure 3, the standard Gibbs free energy change at 20 degrees Celsius and 600 degrees Celsius for the reaction Fe2O3 plus hydrogen to give iron plus water. Given that the standard entropies of iron 2 oxide, hydrogen, iron and water are 90, 131, 27 and 189 joule per Kelvin per mole respectively, and the standard enthalpies are minus 822, 0.0, 0.0 and minus 242 kilojoule per mole respectively. Comment on the feasibility of the reaction. Now in this question, we need to get the equation right. We have it as Fe2O3, which reacts with hydrogen gas to produce iron plus water. And we have the balanced equation, which is 3 over here, and we have 2 here. We have 3 moles of hydrogen gas, and that balances the equation. Here we have a solid, we have a gas, and we have a solid, and here we have a gas. The first part of the question is that we should calculate the standard enthalpy change. And from the question, we are given the enthalpies for each of the reactants and the products. Now, the list of what we have here. For the enthalpies, which is H, we have minus 822. For Fe2O3, we have 0 for hydrogen, we have 0 for iron, and we have minus 242 for water. Then for entropy, we have 90 for we have 90 for iron 2 oxide, and we have 131 for hydrogen, we have 27 for iron, and we have 189 for water. So with all this, now we can proceed to find the standard entropy change. We have that the standard entropy change equal to the standard entropy of the product minus the standard entropy of the reactant. For the product, we have this. Now, for the product, we will take it that 2 multiplied by 0 plus 3 mole of water, that is minus 242. So these are the products. Then minus, for the reactants, we have minus 822 plus, for the other reactant, which is water, we have 3 multiplied by 0. Now 2 times 0 gives 0 plus 3 times minus 243. That gives minus 726. Alright, so 2 times 0 is 0. Then 3 times minus 242. That gives minus 726. Then this minus over here. Then we have minus 822. 3 times 0 is still 0. So we have minus 726. Minus times minus gives us a plus, and then 822. When we find the sum of this, we'll have 96 kilojoule per mole. So this is the standard enthalpy change of the reaction. For the B part, we have to calculate the standard entropy change. And we have that standard entropy change of the reaction equal to the standard entropy change of the product minus the standard entropy change of the reactant. Here are the values we will use. For the products, we take these two. We have 2 moles multiplies 27. The other product is water, which is 3 moles multiplying 189 minus, for the reactants, we have 90 plus, we have 3 moles of hydrogen gas, that is 3 times 131. When we multiply this out, we'll have 54 plus 3 times 189, and that gives 567 minus, so we have 90 plus 3 times 131, that gives 393. And when we find the sum of all this, we will end up having, this will be 621 minus 483, and that is equal to 138 joules per Kelvin per mole. But it will be advisable that we work in kilojoules, because over here we have kilojoules here, and so we have it as 138 divided by 1000, and that will give 0.138 kilojoule per Kelvin per mole. And that brings us to our third part of the question, which is to find the standard Gibbs free energy change at 20 degrees Celsius. So we have it that at 20 degrees Celsius, now we have to work in Kelvin. So when we convert 20 degrees Celsius to Kelvin, we will need to add 273 to it, and we will have 273 plus 20, that's 293 Kelvin. 293 Kelvin is the same thing as 20 degrees Celsius. Next, we have that the standard Gibbs free energy at that temperature equal to delta H minus T delta S. Those are standards. Now for the delta H, we have 96 over here minus the temperature at 20 degrees Celsius, that is 293, multiplied by the delta S. This is the delta S, that is 0.138. Now when we multiply all this out, we will have 55.57 kilojoule per mole. Now this is a positive Gibbs free energy, and when it is positive, we have that it is not spontaneous, so it is non-spontaneous at 20 degrees Celsius. Next, at 600 degrees Celsius, we need to convert that into Kelvin, and that is done by adding 273, and that gives 873 Kelvin. Now, to get the standard Gibbs free energy, which is equal to delta H theta minus T delta S theta, the standard enthalpy equal to 96 minus the temperature, which is 873, multiplied by the delta S, which is 0.138. So we have 96 minus, when we multiply this out, it gives 120.474, and we'll have minus 24.47 kilojoule per mole as the standard Gibbs free energy at 600 degrees Celsius. So now from here we have a negative value of delta G, and a negative value here indicates that it is spontaneous. So a negative value is spontaneous while a positive value is non-spontaneous. Here's the next question, which says that calculate the standard enthalpy changes for the reaction involving the decomposition of hydrogen peroxide to water at 25 degrees Celsius. Given that the standard free energies of hydrogen peroxide, water, and oxygen are minus 120.35, minus 228.5, and 0.0 kilojoule per mole respectively. Here we have our equation, which is hydrogen peroxide, which decomposes into water and oxygen. To balance this equation, we have 2 here and we have 2 over here, and that has balanced the equation. Here we have a liquid and we have gas over here. Now with that, we're told that the standard free energies of hydrogen peroxide, we have it as minus 120.35. For water, we have it as minus 228.5, and for oxygen, we have it as 0. And to find the standard Gibbs free energy change is equal to the standard Gibbs free energy of the product minus the standard Gibbs free energy of the reactant. Now for the products, we have, for water, we have 2 moles of water, so multiply 2 by this, that is minus 228.5. We have oxygen, which is 0, minus, for the reactant now, we have 2 moles of hydrogen peroxide, and so we multiply this 120 by 2. So we have 2 multiplied by minus 120.35. Alright, so 2 multiplies minus 228.5, and that gives minus 457. So we have minus 457 plus 0 is nothing. So we have minus 2 multiplies minus 120.35, and that gives us minus 240.7. So we have minus 240.7. So minus 457 minus times minus gives us a plus, and then we have 240.7. When we add this together, that is minus 457 plus 240.7, that gives minus 216.3 kilojoules as the standard Gibbs free energy of the reaction. A negative Gibbs free energy shows that this reaction is spontaneous. So we have a spontaneous reaction over here.